Have you ever thought about what powers our world? I mean, really powers it. We talk a lot about the sun, wind, and water, which is awesome. But there's another source of energy, a really powerful one, that comes from deep inside the earth. It comes from a special kind of metal called uranium. Now, uranium isn't like the iron in your breakfast cereal or the aluminum in a soda can. It's a super heavy element, one of the heaviest that exists naturally on our planet. It's packed with an incredible amount of energy, more than you could ever imagine. This isn't the kind of energy you get from burning something, it's nuclear energy, the energy stored inside the very heart of an atom. So, what makes uranium so special? It's all about its atoms. An atom is the tiniest building block of everything, and it has a center called a nucleus. Uranium's nucleus is big, wobbly, and a little unstable. Think of it like a tower of blocks that's been built just a little too high. It doesn't take much to make it tumble. Like when a uranium atom's nucleus breaks apart, a process we call fission, it releases a tremendous burst of energy. This single tiny event is the key to everything from lighting up entire cities with nuclear power to creating some of the most powerful weapons ever known. Uranium is truly the heavy hitter of the periodic table, and its story is one of discovery, power, and responsibility. The journey of uranium is a fantastic scientific adventure that has completely reshaped our understanding of the universe and our place in it. For a long time, this element was hiding in plain sight, used for centuries without anyone knowing its true potential. People just thought it was a neat rock that could make pretty colors. But once scientists started to look closer, they unlocked a secret that would change the course of human history forever. It led to brand new fields of science, transformed medicine, and gave us a powerful new way to generate electricity. It's an element that carries immense promise for a clean energy future, but also one that demands our utmost respect and caution. Understanding uranium is about more than just science. It's about understanding our own world. The decisions we make about how to use this powerful element affect everyone on the planet. From international politics and environmental policies to the electricity that comes out of your wall socket, uranium's influence is everywhere. It's a story filled with brilliant scientists, world-changing discoveries, and tough questions that we're still trying to answer today. So let's get ready to explore this amazing element. We'll look at where it came from, how we discovered its secrets, and how it continues to shape our lives in ways you might not expect. It's going to be a wild ride. Long before we knew what an element was or what an atom was, people were already using uranium. They just didn't know it. Our story starts way back, almost 2,000 years ago in the Roman Empire. Archaeologists found a beautiful piece of colored glass in a Roman villa near Naples, Italy. The glass had this amazing yellowish-green color, and when scientists analyzed it in modern times, they were stunned. The pigment that gave the glass its vibrant hue was uranium oxide. The Romans had unknowingly used a tiny amount of this radioactive material to make decorative art. For centuries, miners in places like Bohemia, in what is now the Czech Republic, would find this heavy, dark mineral they called pitchblende, but they mostly just tossed it aside as useless junk. For hundreds of years, that's all pitchblende was, a waste product from silver mines. Miners were looking for valuable metals, and this black rock just got in the way. It was also used by glass makers in the region who had perfected the art of creating stunning colored glass. They called it Bohemian glass, and it was famous for its rich, deep colors. By adding a little bit of processed pitchblende to their molten glass, they could create beautiful shades of yellow and green that seemed to glow under the right light. They had no idea that this glow was a hint of the incredible power locked inside the mineral. They were just artists and craftspeople using a natural pigment to make the world a more beautiful place. The first big step toward understanding what this mysterious substance really was came in 1789. A German chemist named Martin Heinrich Klaproth was examining a sample of pitchblende. Klaproth was a meticulous scientist, known for his careful and precise experiments. He was convinced that this strange mineral contained a new, undiscovered element. Through a series of chemical reactions, he managed to isolate a yellow compound which he believed was the pure metal. He decided to name this new element uranium in honor of a very recent and exciting astronomical discovery. The planet Uranus, which had been spotted by William Herschel just 8 years earlier. Klaproth was celebrating science, linking a discovery on Earth to a discovery in the heavens. However, Klaproth hadn't quite gotten it right. What he thought was pure uranium metal was actually uranium oxide, a compound of uranium and oxygen. It was still a monumental discovery, but the final step was yet to come. it would take another 52 years for someone to isolate the true metallic uranium. In 1841, a French chemist named Eugène Melchior Peligot took on the challenge. He realized that Klaproth's substance was an oxide. By reacting uranium tetrachloride with potassium, Peligot succeeded where Klaproth had not. He was the first person to produce a sample of pure, silvery gray uranium metal. Finally, the element stood on its own, revealed to the world, though its greatest secrets were still waiting to be uncovered. For decades after its discovery, uranium was mostly a scientific curiosity. It was used to color glass and ceramics, creating beautiful Vaseline glass that became popular in the Victorian era because of its strange, beautiful glow under ultraviolet light. But nobody suspected it was anything more than a heavy metal with some interesting coloring properties. That all changed in 1896, thanks to a French physicist named Henri Becquerel. He was studying materials that could glow in the dark after being exposed to sunlight, a phenomenon called phosphorescence. He wondered if the phosphorescent glow from uranium salts could be related to the newly discovered X-rays, which could pass through solid objects. His experiment was simple. He planned to wrap a photographic plate in thick black paper so no sunlight could get in. Then he would place a chunk of uranium salt on top and leave it in the sun. His theory was that the sunlight would make the uranium glow, and this glow would emit rays that could penetrate the paper and expose the plate. But science is full of happy accidents. One day the weather in Paris was cloudy, so Becquerel couldn't do his experiment. He put the wrapped photographic plate and the uranium salt away in a dark drawer and decided to wait for a sunny day. A few days later, for some reason, he decided to develop the plate anyway. He was absolutely astonished by what he saw. The plate had a clear, strong image of the uranium chunk on it, as if it had been exposed to a bright light. But it had been in total darkness the whole time. The sun had nothing to do with it. The uranium itself was emitting some kind of mysterious, invisible rays that could pass right through the thick paper. Becquerel had accidentally discovered a completely new phenomenon. These rays weren't coming from an outside source like the sun. They were coming from the uranium atoms themselves. He had discovered what we now call radioactivity. It was a revolutionary idea that an element could spontaneously pour out energy all on its own, without being heated, burned, or zapped with electricity. Becquerel's discovery opened the floodgates of scientific inquiry. A brilliant young scientist in Paris named Marie Curie became fascinated by his work. Along with her husband Pierre Curie, she began a systematic search for other elements that gave off these strange rays. They tested every element they could get their hands on. They soon confirmed that thorium was also radioactive and discovered that the intensity of the radiation depended only on the amount of uranium or thorium present. It was a property of the atom itself. Their work led them to discover two new, even more radioactive elements, polonium and radium. The Curies coined the term radioactivity to describe this amazing phenomenon, and their work earned them a Nobel Prize, forever changing our model of the atom from a solid, unbreakable sphere to a dynamic and energetic world. The discovery of radioactivity was just the beginning. Scientists now knew that atoms contained immense energy, but honestly, they had no idea how to release it on a large scale. The key to unlocking this power was discovered in 1938, in a laboratory in Berlin. Two German chemists, Otto Hahn and Fritz Strassmann, were bombarding uranium with neutrons, which are these tiny particles found in the nucleus of an atom. They were expecting to create even heavier elements, but their results were, well, baffling. When they analyzed their samples, they found traces of barium, a much lighter element. It was as if the uranium atom had been split in half. They didn't know what to make of it, and wrote to their former colleague, Lisa Meitner. Lisa Meitner, a brilliant physicist who had been forced to flee Nazi Germany, received their letter in Sweden. While discussing the strange results with her nephew Otto Frisch, she had a flash of insight. They realized that the uranium nucleus wasn't just chipping a piece off, it was actually splitting into two smaller nuclei. They calculated the energy that would be released in this process, and found it was enormous. Exactly as predicted by Albert Einstein's famous equation, E equals mc squared. Meitner and Frisch called this process nuclear fission. The news spread like wildfire through the scientific community. Scientists everywhere immediately understood the implications. If a splitting uranium atom also released more neutrons, those neutrons could go on to split other uranium atoms, creating a chain reaction that would unleash an unbelievable amount of energy. This groundbreaking discovery came at a terrifying time in world history. World War II had just begun, and many of the scientists who understood fission were refugees who had fled fascism in Europe. They were deeply worried that Nazi Germany might be able to use this new knowledge to build an atomic bomb, a weapon of unimaginable destructive power. In 1939, a group of concerned scientists, including Leo Szilard and Albert Einstein, wrote a letter to U.S. President Franklin D. Roosevelt. They warned him of the danger and urged the United States to start its own research program before it was too late. This letter was the catalyst for one of the largest and most secret scientific undertakings in history. In response, the U.S. government launched the Manhattan Project. It brought together some of the brightest scientific minds in the world, including Robert Oppenheimer, Enrico Fermi, and Richard Feynman. Their mission was to build a functional atomic bomb. They built entire secret cities, like Los Alamos, New Mexico, and Oak Ridge, Tennessee, dedicated to enriching uranium and designing the weapon. On July 16, 1945, in the desert of New Mexico, they conducted the Trinity test, the world's first atomic detonation. The mushroom cloud that rose over the desert signaled the dawn of the atomic age. Less than a month later, atomic bombs were used on the cities of Hiroshima and Nagasaki in Japan, effectively ending World War II, but forever changing the nature of warfare and international politics. After the devastation of World War II, scientists and leaders around the world began to ask a critical question: could this incredible atomic power be used for good? The same process of nuclear fission that could create a bomb could also be controlled to generate heat. This heat could boil water, create steam, and turn turbines to generate electricity. This was the idea behind President Dwight D. Eisenhower's Atoms for Peace speech in 1953. He proposed a shift in focus, from building atomic weapons to using nuclear energy for peaceful purposes, to provide electricity for a growing world. This initiative sparked the development of the global civil nuclear power industry. The first nuclear power plant to generate electricity for a public grid came online in Obninsk, Soviet Union, in 1954. It was a small-scale reactor, but it proved the concept was viable. A few years later, in 1957, the Shippingport Atomic Power Station in Pennsylvania became the first full-scale commercial nuclear power plant in the United States. The idea was revolutionary. A small amount of uranium fuel could produce the same amount of electricity as millions of tons of coal or barrels of oil, and it could do it without releasing greenhouse gases like carbon dioxide. For many, nuclear power seemed like a miracle technology that would provide clean, cheap, and virtually limitless energy for all of humanity. Beyond generating electricity, uranium's radioactive properties found many other peaceful applications that have transformed our lives. In medicine, radioactive isotopes derived from nuclear processes like technetium-99m are essential for diagnosing diseases. They act as tracers that doctors can follow through the body to see how organs are functioning, helping to detect cancer, heart disease, and other conditions. Radiation therapy, using controlled beams of energy, has also become a cornerstone of cancer treatment, targeting and destroying cancerous cells. In industry, radioactive materials are used to sterilize medical equipment, irradiate food to kill bacteria and prolong its shelf life, and inspect welds and machinery for flaws without taking them apart. Science itself has also benefited immensely. Nuclear reactors are not just for power, they are also powerful research tools. They produce beams of neutrons that scientists can use to study the atomic structure of materials, leading to advances in everything from new medicines to stronger metals and more efficient batteries. Archaeologists use a technique called carbon dating, which relies on understanding natural radioactivity to determine the age of ancient artifacts. Uranium and its decay products are also used to date geological formations, giving us incredible insights into the history of our planet. The peaceful atom, powered by uranium, has become an indispensable part of modern science, industry, and medicine. Uranium is the ultimate double-edged sword. On one hand, it holds the promise of a clean energy future. Nuclear power plants, which run on uranium, generate a massive amount of electricity on a very small land footprint, and crucially, they do this without producing the greenhouse gases that contribute to climate change. In a world desperately trying to move away from fossil fuels like coal and oil, nuclear energy offers a reliable, powerful, and carbon-free source of electricity. It can run 24 hours a day, 7 days a week, providing the steady baseload power that solar and wind energy, which are intermittent, cannot always guarantee. This makes uranium an incredibly important tool in our fight against global warming. However, the other edge of the sword is sharp and dangerous. The very same properties that make uranium so powerful also make it hazardous. The radioactivity it emits can be harmful to living things, if not handled with extreme care. Exposure to high levels of radiation can cause severe illness and can damage DNA, leading to an increased risk of cancer. This is why the entire nuclear fuel cycle, from mining the uranium ore to processing it into fuel rods, must be managed under the strictest safety protocols. Workers must be protected with shielding and monitoring equipment, and the entire process is heavily regulated to prevent any accidental release of radioactive material into the environment. The greatest fear associated with nuclear power is the risk of a major accident. Events like the meltdowns at Chernobyl in 1986 and Fukushima Daiichi in 2011 are seared into public memory. These accidents, caused by a combination of flawed design, human error, and natural disaster, released radioactive materials into the environment, forcing mass evacuations and causing long-term health and environmental consequences. While such catastrophic failures are extremely rare in the history of the industry, their potential severity means that safety is the absolute #1 priority in the design and operation of every nuclear reactor. Modern reactor designs incorporate multiple layers of redundant safety systems to prevent such accidents from ever happening again. Another significant challenge is what to do with the nuclear waste. After uranium fuel is used in a reactor, it remains highly radioactive for thousands of years. This spent fuel must be safely stored and isolated from the environment for geological timescales. Finding a permanent solution for nuclear waste disposal is a complex scientific and political problem that countries around the world are still working on. Proposed solutions include deep geological repositories, where the waste can be buried thousands of feet underground in stable rock formations. Balancing the immense benefits of nuclear energy with the serious responsibilities of ensuring safety and managing waste is the central challenge of the nuclear age. Today, on January 22, 2026, uranium's role is more important and more debated than ever before. As nations grapple with the urgent need to reduce carbon emissions and achieve energy independence, nuclear power is undergoing a major reevaluation. It stands as one of the few proven technologies that can deliver vast amounts of clean, reliable electricity. Major uranium-producing countries like Kazakhstan, Canada, and Australia are central to the global energy supply chain. The decisions made in these countries about uranium mining and export have a direct impact on the energy security and climate policies of dozens of nations, from France and China to the United States, all of whom rely on nuclear power. The importance of uranium extends far beyond just keeping the lights on. Its applications in medicine continue to save lives every single day. The radioisotopes used in millions of diagnostic scans and cancer treatments each year are a direct legacy of the nuclear science that uranium helped pioneer. In research, uranium and other nuclear materials are helping us develop new technologies, from advanced materials for aerospace engineering to more resilient crops for agriculture. The global framework that governs uranium, managed by organizations like the International Atomic Energy Agency, is a cornerstone of international diplomacy, focused on preventing the spread of nuclear weapons, while promoting the safe and peaceful use of nuclear technology. Looking to the future, uranium will likely continue to be a key player. Scientists and engineers are developing next-generation nuclear reactors that are smaller, safer, and more efficient than ever before. Some designs, known as small modular reactors, could be built in factories and deployed to power remote communities or industrial sites. Other advanced designs aim to burn nuclear waste, reducing its long-term radioactivity and extracting even more energy from the original uranium fuel. These innovations could make nuclear power an even more attractive option for a world that needs more clean energy, and fast. Uranium's journey is far from over. It is evolving to meet the challenges of the 21st century. From its humble beginnings as a pigment for coloring glass, to its terrifying debut on the world stage as a weapon and its ongoing role as a powerful source of clean energy and life-saving medicine, uranium's story is a reflection of our own. It shows our capacity for brilliant discovery, our struggle with immense power, and our ongoing quest for a better and more sustainable future. This single, heavy element forced us to confront the deepest secrets of the atom, and in doing so, to confront fundamental questions about our own survival and progress. The path forward requires careful science, thoughtful policy, and a global commitment to harnessing its power responsibly for the benefit of all. From a simple color in Roman glass to the element that would define an age, uranium's journey is the story of how one substance changed the world.